Swayam Prabha. Digital India. Educated India.
We have already seen the kind of the natural response we will get from a second order circuit when we have real and distinct roots for the characteristic equation. We will get two exponentials. Now if we have real but coincident roots, we've already seen it, but I'll just show it anyways. In this case, P1 will be equal to P2 and each of them will be equal to 1 over square root LC. Okay, and in this case the response, the natural response will be, of course this is for our usual R L C circuit. The natural response for VC is going to be A1 plus A2t exponential minus t by square root LC. This is basically exponential P1t. Okay. Now, how do you determine the constants A1 and A2? As usual, it is by applying the initial conditions. Okay, we will have initial conditions Vc of 0 and IL of 0. We know that IL of t, which is the current in the inductor, is the same as the current in the capacitor, so it is C times dVc by dt. Okay, so IL of t will be C times the time derivative of this, which is A1 plus A2t times P1 exponential P1t. This is just chain rule. First I am differentiating this part of it, plus A2 times exponential P1t. Okay, so from the first one we will get Vc of 0 to be A1, and from the second one we will get IL of 0 to be C times A1 P1 plus A2. We have two equations in two unknowns and we can find both A1 and A2. Okay. Now when we have complex conjugate roots, we will have P1 and P2 to be some real part plus minus j times the same imaginary part. Okay, and the real part will be minus R by L. The imaginary part, you know the expression for. This will be plus minus j times square root of 1 over LC minus R by 2L squared. Okay. So again the response will be of the form A1 exponential P1t plus A2 exponential P2t. Now in this case P2 is of course P1 conjugate, so A2 will also be A1 conjugate, so that the whole expression is real. Okay. Now if I substitute the form of P1 and P2, I'll have PR times T plus J Pi times T plus A1 conjugate exponential PR times T minus J Pi times T, which after factoring out exponential PRT outside, we'll have exponential JPIT plus A1 conjugate exponential PRT exponential minus J PIT. Okay. This is a real number, exponential PRT, and is common to the two terms here. Now the other part, you can see that we have A1 times exponential JPIT, it's some complex number. The other part, A1 conjugate times exponential minus JPIT, is also a complex number, and it is the complex conjugate of the first one. Okay. Now the most convenient way to simplify this further is to represent A1 in polar form. So let's say A1 is the magnitude of A1 exponential J times the angle of A1, whatever that is. Okay. Substituting that, what we will get is Vc of t is the magnitude of A1 exponential PRT. This will be a common factor to the whole thing, and then we'll have exponential J PIT plus angle of A1 plus exponential minus J PIT plus angle of A1. Okay. And you realize that this is nothing but 2 times cos PIT plus angle of A1. Okay. So this whole thing can be written as 2 times absolute value of A1 exponential PRT and cos PIT plus angle of A1. Okay. So again you have 2 constants. You can think of them, originally we had A1 and A2. Now we have A1 and A1 conjugate, but A1 itself has the real and imaginary part, A1R and JA1I, or the magnitude and the angle. Okay. So you can represent that in any way you want, but finally you will have 2 equations from 2 initial conditions, and you can find these 2 numbers. Typically it is easiest, we can, this 2 doesn't have much significance here. This whole thing is some constant A0 exponential PRT cos PIT plus some angle phi. So we have 2 constants A0 and phi, which you can find from the initial conditions. Okay. So these are the responses when you have real coincident roots and when you have complex conjugate roots for the characteristic equation of the second order system. Okay.